Okay, so natural series RLC circuits. Let's just start that. Series RLC circuits. So first, of course, we are going to discuss the natural response as we discuss the natural response of the parallel RLC circuits. And then later on today, we are going to start the complete response. That is, when you have source in the circuit after the change happened, like we did with RC circuit and RL circuit. First, we discussed the natural response and then the complete or the forced response. So we are going to do the same thing with RLC circuits as well. But starting with the series RLC natural response, let's assume we have a series RLC circuit. And let's assume the circuit was running for a long time. There was some voltage across the capacitor. There was some initial current in the inductor that we represent, of course, initial value at t is equal to 0 in general. So VC, VL, VR. And since the current is same across each component, let's just call this current I. We can also call it IL because, of course, the current is passing through inductor and inductor current does not change instantaneously. But let's just call this current I. So when we are writing the KVL equation, what will be the KVL equation around the loop if I want to write the KVL equation? It's going to tell me that. Sum of the voltages is 0. So the KVL equation is going to be VR plus VL plus VC is equal to 0. Okay, in terms of current now, remember we are trying to find the current. In terms of current, now we have to write this KVL equation. So VR is, in terms of current, VR is I times R, of course, VL LDI or DT. And finally, VC. One over C, yeah. 1 over C integral of I dt plus the initial value of the capacitor voltage VC 0 also 0. And this is equal to 0. And as we did for the parallel natural circuits, we have to get rid of the integral. So we are going to differentiate this equation one more time. And we can write this down as R di over dt plus L d2I over dt square. And then when we differentiate this, it's gonna take care of the integral and we're gonna be left with I over C. And of course, differential of the constant value, VC0 positive will be 0. And that will be equal to 0. Let's write this equation down in the highest to lowest power of the differential and then get rid of the coefficient associated with the highest power of the differential. So we're going to write this down as d2I over dt squared. Divide the whole equation by L to get rid of this L plus R over L di over dt plus I over LC equals. And again, like we did for the parallel circuit, we assume that since I is the current, which we can assume to be the inductor current because inductor is connected, and we know the inductor current changes exponentially in the natural circuit, right? Once the inductor is charged, then the inductor current, it changes exponentially when it is discharging. So we will assume the same thing. We're going to assume that let IT, which is ILT, can be given by A e to the power ST. It's an exponential function. Since inductor current changes exponential. So same thing we assume for parallel RLC circuit, we assume that the voltage across capacitor change exponentially. So we assume that VCT can be given by a generic equation as a generic equation A e to the power ST. In this case, S is, of course, if it is discharging, it's a negative value. So we're going to go ahead, and if we assume that this is a solution of the inductor current, we're going to go ahead and plug in that solution in the differential equation. And then we're going to differentiate. So what is the second order differential of A e to the power ST? A is constant, of course. Yes. Go ahead. S square e to the power st. Very good. So first order differential is going to be S e to the power st. And the second order differential is going to be one more S e to the power st. So S square e to the power st plus R over L differential of this again is going to be S e to the power st plus A e st over Lc. A e to the power st is common in each term, so we're going to take it as a common factor. That will leave us S square from the first term, R over L S from the second term, and 1 over Lc from the third term. And this is equal to 0. And once again, we will see both both values that are multiplying each other. So this AEST times S square plus R over Ls plus 1 over Lc, and we will say that either of these values will be 0, then the product on the left hand side will be equal to the right hand side. Both will be 0. Of course, since A e to the power st is the solution that we have assumed, that cannot be 0. That's how inductor discharges. So the first term cannot be 0. That means the second term has to be 0 in order for the equation to be balanced. So since A e to the power st is a solution, it cannot be 0. Therefore, S square plus R over Ls plus 1 over Lc is equal to 0. And that is what we call this equation. Anybody remember? Characteristic equation. This is the characteristic equation of the differential. So we're going to solve this equation to find the two roots. It's a quadratic equation. So the two roots S1 and S2 will be negative B. B is R over L plus minus B square R over L square minus 4AC minus 4A is 1 and L over C divided by 2A divided by 2. And we're going to take this 2 in the numerator. It's going to become negative R over 2L plus minus, when this 2 is going to go in the under the square root, that's going to become 4. So R over 2L square. 2 is going to become 4, of course. And then this 4 is going to cancel out this 4 when I take this 2 under the square root for this term, which will leave the last term to be 1 over LC. And this is our familiar equation. This is negative alpha plus minus alpha square minus omega naught. In this case, the only thing that is different is alpha. Napier frequency is R over 2L. What was the Napier frequency for the RLC circuit parallel? 1 over 2 RC. 1 over 2 RC for parallel RLC circuit and R over 2L for series RLC circuit. So that's the only thing that is different. Everything else is the same. The process is the same. Omega naught, of course, is the same. Omega naught is resonant frequency. And it is the same equation 1 over square root of LC. We have again 3 damping types. Alpha greater than omega naught, overdamped circuits. And for overdamped circuit, the expression is going to be the same as the voltage. The current expression is going to be A1 e to the power S1t plus A2 e to the power S2t. Scroll up. All 3 damping dynamics, exactly. Because anytime you have both L and C in the circuit, you will always have damping. And damping types are going to be overdamped, underdamped, critically damped. Underdamped circuits are the most employed circuit in the real world, actually. The sinusoidally decaying response that is used in control systems, in your rides, everywhere. Most of the circuits that are used, RLC circuits, they are underdamped circuits. But the damping types, of course, there are 3 damping types. But underdamped is the most commonly naturally found damping in RLC applications. Yeah, I'm sorry. Yeah, characteristic roots of the characteristic equation, or just the characteristic equation. Oh, this. So this I'm taking here, right? So this is 2L, and when Gloriana, when 2 is going to go in the square root, so in the square root, 2 is going to become 4, right? Under a square root of 4 is 2, right? So when I take this 2 in the square root, it's going to become 4. So that's going to be 4 because I'm taking a square of that, 2 squared. And then this is going to be 4 here, and that 4 and this 4 will be cancel each other. And it's going to be 1 over LC. The second type, of course, is underdamped circuit. Alpha is less than omega naught. IT will be equal to A e to the power negative alpha t, a cosine, a1 cosine omega dt plus a2 sine omega dt. That's the underdamped response. Omega d, of course, is, let me write down. Omega d is square root of omega naught square minus alpha square. When you have the square root becomes imaginary, then you take that I outside, you flip omega naught and alpha, and that becomes natural resonant frequency. That's a frequency of the sinusoid that is oscillating and decaying. And this is natural resonance. And finally is the critically damped circuits. When alpha and omega naught are equal, and of course the response is e to the power negative alpha t, a1 plus a2t, or a1t plus a2, whatever you want to write. So these will be a generic response type. Again, our goal is to find first what type of damping is there in the circuit, and then we're going to find the values of a1 and a2 using initial conditions first, and then we're going to differentiate the equation of the current with respect to time, and then evaluate that equation, the differentiated equation, at the initial condition to find the second variable. So it's the same process that we followed for the parallel RLC circuit. Everything is the same. Of course, circuit analysis you will have to perform, as especially when you are doing the initial condition after you differentiate the equation. Then you have to see, what voltages are making up this or that, like we were doing in the parallel RLC circuit. What current is this? What current is that? Yes, the rest? WDT, yeah. WDT. Should put it in parentheses. WDT. WDT. So in your, if you're writing a MATLAB code, and if you have written a MATLAB code, which I highly encourage you to do that for the parallel RLC transient circuit to calculate alpha, omega naught, and all those things, S1 and S2, just copy that code for the series. The only thing that you're changing is the equation for alpha. From 1 over 2 RC, it become R over 2L. That's the only difference. So it's exactly the same code except alpha. All right, I'm going to open my MATLAB as well so we can start solving some problems. So keep the parallel resistance program with you in MATLAB. Keep the parallel RLC circuit code with you. Keep the series RLC circuit code with you. All of these codes you are allowed to use in exam and quizzes whenever. Because again, that's just to help you solve the problem. Of course, you still have to analyze the problem. If your analysis is incorrect, irrespective what you're doing, everything is going to be incorrect. So analysis is the main thing, but after analysis, to speed up the solution process, it's always wise to take help of programming, because that's not going to change. Your equations are, as long as your equations are correct, you will get the correct result through MATLAB or Octave or whatever you're using. Okay, so we're going to start solving some problems. Let's say problem. Okay, let's assume we have Yes. Uh-huh. Alpha equation, yes. R over 2L. Instead of 1 over 2 RC, R over 2L. Okay. Or actually, I'll just use that so that we can use it. Now, when the circuit is given to you, remember the first, make sure you observe the circuit. Observe if it's a natural circuit or if it's a forced circuit, complete response, observe. If it's a parallel circuit or it's a series RLC circuit. That's extremely important because if you don't observe it and your conclusion will be that you're going to make series parallel and parallel series, then everything is going to be incorrect. And again, I see, of course, in tests and quizzes and stuff, you guys still struggle with what is parallel and what is series. That struggle should go away, guys. Parallel, look at the nodes. If components are connected between the same nodes, those components are parallel. If you see that they don't share same nodes, they cannot be parallel. Likewise, series, same current has to flow through all those components if they are in series. If you get to a junction and you see current is dividing, then the components are not in series after the current is divided. So please do not make mistake in parallel or series because I see many of you are still making those mistakes. Also realize that if there's an open circuit, if there's a component there, if there's no current flowing through that component resistor or something, that resistor is not part of the circuit in that case. Throw that resistor away. So when a circuit like this is given to you and the question is simply determine ILT and VLT for t greater or equal to 0 positive, your first you're going to observe, okay, well, the change is happening, of course. What is the change that is happening in this circuit? Who's going to tell me? Yes, Mike. What change is happening in the circuit? Say it again. Yeah, tell me what change is happening in the circuit. Oh, okay. Well, no, that's not what I'm asking. I'm asking, you see this circuit, and if I ask you, in this circuit, a change is happening, and I'm asking you, what is the change that is happening in the circuit? Give me a second. Then what is that change that is happening in the circuit? Zora, what is the change that is happening in the circuit? Okay, so mhm. Mhm. Okay, so that's the change. That's what I'm asking. That's a change that is happening in the circuit, that when T is negative, the current source is in the circuit, and when T becomes 0 or positive, the current source becomes open circuit. That's a change that is happening in the circuit. So you have to identify the change that is happening. You have to identify the time at which the change that is happening. The change is happening at T is equal to 0. Before the change, current source is in the circuit. It is active. Assume it's running for a very long time, even if it is not given to you. Assume the circuit is at a steady state. It is running for a very long time. And from that, find the initial conditions. So that's what we are going to do. The first thing, we find the initial conditions. At T is 0 negative, or T less or equal to 0, but specifically just before the change happens, at T is equal to 0 negative, we are going to find IL0 negative, which will be equal to IL0 positive, and VC0 negative, which will be equal to VC0 positive. Okay, so who is going to tell me now what will be IL0 negative? Give me a second. IL0 negative. This should not take that long to determine what is IL0 negative, because 2 ampere, why? Okay, capacitor is open, inductor is short, capacitor is open. So all the current is just going to flow in this loop. Capacitor is open, so no current is going to go through that. So 2 ampere. All right, what about the capacitor voltage? What will be the capacitor voltage? Yes, Natasha. Say it again. I don't think I get you. Current divided by what? Okay, I just said that make sure when you say anything that it is parallel or series, make sure you analyze that if you're saying they're parallel, they are connected between the two same nodes. Are R1 and R2 connected between the two same nodes? Yes. So you're saying that R2 is connected here between this node and this node, and you're saying R1 is also connected between these two nodes. Okay, so they're not in parallel. Okay, so yes, go ahead. R1 what? 2 divided by R1. So I over R, what is that formula? I over R. I don't think that's any formula. Yes, there is. Two times R1 is going to be voltage across R1, remember. That's going to be the voltage. That's going to be the voltage here. If you think this voltage is the same as VC, then it's going to be 2 times R1. If not, then it's not going to be that. Yes, Gloriana. Okay, that's not it. Lazaro, what will be the voltage across capacitor? Okay, so what is that? We're looking for VC. Mike, you have an answer? It's the R2 exactly. It's the voltage across R2. Remember, L is short. So R2 is going to become parallel to VC if L is short. The same current flowing here, the voltage drop here, there is no voltage drop here. So the voltage drop here is basically the voltage between this node and this node, as this is short circuit. Go ahead. Go ahead.
So why did we go for R2 is when the inductor shorts,
Yes.
the R2 is left hanging.
No, it's a short. You replace it by the short, the Y. You just, right? Yeah. So it's a voltage across R2. And that is going to be I times R2. 2 times 6, 8, 12. 2 times 6, 8. So these two values are the initial values for the current as well as the voltage. Yes, sir. Capacitor is open, inductor is short. Yes. Yep. So R1, I put down the voltage, VR1 right there. You can see that voltage is not equal to VC. You can see that on the circuit, you can see that they are not equal. Because if you're running a KVL in that loop on the left side, it's going to be the voltage across the current source equals VR1 plus VC, right? So VR1 and VC are not equal. Now, when the current is flowing through R2, which is the same current as IS because capacitor is opened, when the current is passing through R2, there is no voltage drop in L. It's short. So all the voltage that is going to be dropped in R2, that voltage is going to be from that node, the green point that I put over there, and at the bottom node because L is short out. So you can replace L by a short circuit, a wire, right? So R2 is virtually, not physically, but virtually be connected between the same node as capacitor is connected. Because you take the resistor, take the inductor out, replace it by a short circuit, right? So that becomes the same node as the bottom node. So R2 will be connected in parallel with VC. Therefore, the voltage drop across R2 is going to be the same as the voltage across VC. So again, that's a mistake that you guys are making over and over again, that without looking at the proper nodes, you declare something parallel or something, but they're not parallel. So please stop making that mistake. Observe very carefully if they're connected between the same nodes or not, and then say they're parallel or they're series or something. Okay, and now we're gonna look at, of course, t greater or equal to 0. And at that time, the current source is going to be inactivated. That means it's going to become open. Now, when it will become open, yes, current source, open. Voltage source becomes short. Current source become open, right? So current source is going to become open, which means now R1 is gone, right? Because now it's hanging in the air. There is no current passing through R1. This is open. So now you are left with what? Series RLC circuit. We see R2 and L. And the energy that is stored in the capacitor and the inductor, that energy now is going to rotate current in this circuit. It's going to exchange, the energy is exchanged between capacitor and inductor, as well as it is dissipated through R2. And eventually all the energy is going to be dissipated through R2. And the current is going to go down to 0, as well as voltages will go down to 0. So let's draw the circuit first. This is the natural circuit. And can just write down. we can still assign the same, although the capacitor eventually is going to change its polarity. But initially, the capacitor polarity is going to be the same, since capacitor voltage cannot change instantaneously and inductor current cannot change instantaneously. So initially, capacitor will start dissipating its energy, and then inductor is going to start charging the capacitor in the opposite direction until it is fully charged, during which inductor is going to be dissipating its energy. Okay. So now we have to solve for VL and the current I, which is IL basically. So we're gonna go ahead and find the damping type. Let's go ahead and find the damping type. Yes. The current source becomes open when it is 0. Yes. Oh. So, okay. What are the values? This is my 6 ohm, 6, and L is 2, and C is 0.5. Let's go ahead and copy this. Okay, so these are the results. Alpha is 1.5 radian per second, omega naught is 1. That means this is an overdamped circuit. Omega d, of course, in this case, we don't really use omega d since it's not an underdamped circuit. And of course, FD and TD, we don't really need that either. So since it's an overdamped circuit, the current expression is going to be A1 e to the power S1t, which is this. I'm just going to keep it as S1. We have these values here, plus A to the power A to e to the power S2. S1 is negative 0.38, S2 is negative 2.61. Another question to you guys. Which root is the dominant root? That is, which root is going to define the shape of the response? S1. S1 is going to define shape of the response because the time constant associated with S1, which will be 1 over S1, is going to be larger as compared to time constant with S2, which is 1 over 2.6, which is going to be smaller. So the term associated with S2 is going to die faster as compared to the term associated with S1. Although both are close to each other, 0.38 and 2.6, but S1 is still going to be considered as the dominant root. The closer it is to 0, that's the dominant root. The closest to the 0 is the dominant root, basically, right? Because the time constant corresponding to that frequency is going to be the larger time constant. And the larger the time constant means it's going to take longer to decay. To get to the 36% of the peak value, it's going to take longer amount of time. Okay, how do we find A1? initial condition at t is equal to 0 positive, I 0 positive is going to be a1 plus a2. When you put 0, e to the power 0 will be 1. So both e to the power s1t, e to the power s2t are going to become 1. So you're going to have I0 positive is 2 ampere, the current. So the first equation is a1 plus a2 is equal to 2. And to find the second equation, we are going to differentiate it with respect to t and then put t is equal to 0 positive also. And that's going to give us a1 s1 e to the power s1t plus a2 s2 to the power s2t. And once again, guys, no need to put the values of s1 and s2 and a1, a2 right now, because as long as they're in terms of variable, they're clean. You can do whatever. Of course, you have the values. Anytime you need the values, you can go ahead and plug them in. But in terms of variable, everything is always very clean when you are doing the derivation. So keep everything in terms of variable until you get to the last step, and then plug in the values. Okay, and now we're gonna evaluate this again at 0 positive. And that will give us a1 s1 plus a2 s2. Again, e to the power 0 will be 1. Okay, now di over dt. How are we going to write that down? Di over dt. And remember, this current is inductor current, so it's actually dil because it's passing through inductor. VL over L. VL over L. Okay, now you go back to the circuit and then see what is VL. So this is VL, this is VR, and this is VC. You can change the polarity of VC if you want, but the value of VC, the initial value, was calculated in this direction. So if you're changing the polarity, make sure the initial value is going to become negative. It doesn't really matter whichever direction you choose. The value is going to be either positive or negative based on the direction. So what do you think VL equation is going to be? Okay. So negative VC plus VR plus VL is equal to 0. So VL is equal to VC minus VR. Again, if you keep the same polarity, I'm just gonna delete that. So positive VR, positive VL, negative VC equals 0. That means VL is equal to VC minus VR. Negative VC plus VR plus VL. So we're going to go ahead and use this equation here. VC0 positive minus VR0 positive over L. Yes. Okay, we have the value of VC0 positive that we calculated, which was 12 volt. Who is going to tell me what will be VR0 positive? How are we going to calculate VR0 positive? Yeah, current passing through the resistor at 0 positive times R, Ohm's law, of course. And we know what current is passing through the resistor at 0 positive because we calculated that current is 2 ampere. So we can easily write that equation down as again VC0 positive minus I0 positive times R over L A1 S1 plus A2 S2. And that will be our equation number 2. Let's see what value that is going to be. So VC0 positive is 12. I'm just going to write down 12. 12 minus I0 positive times R. I0 positive was 2. 2 times R divided by L. So that's coming out to be 0. But that's not really good because the first one is 0 as well, right? No, first one is 2. Okay, but that's fine. Confirm if this is coming out to be 0. 0? Yeah, it's a short. Yeah, well, it's the same voltage, and then inductor is acting initially as a short circuit. I'm sorry? Uh-huh. Mm-hmm. So we're going to go ahead and solve equation number 1 and equation number 2 now. A1 plus A2 is equal to 2, and A1S1 plus A2S2 is equal to 0. So let's go ahead and solve this. So my A is 1, 1, and the second is S1, S2, and then my constant is 2 and 0. So my values for A are A backslash K. So I'm just gonna put this, you know. So my coefficient matrix is, I should have called something else except A, but anyways, coefficient matrix is 1 and 1 from the first, 1 and 1, and from the second is S1 and S2, S1, S2. So this is my coefficient matrix, and my constant vector is 2 from the first one, 0 from the second. So my values of A1, A2, I saved them in Q. So this is my A1, and this is my A2. So my IT is now A1's 2.3416 e to the power S1. Let me see, S1 is what? S1 is negative 0.3820, negative 0.3820, 382T. And then my A2 is negative 0.3416 e to the power negative 2.6182. Negative 2.61 ampere for T greater or equal to 0. That's the current passing through the inductor. Yeah. Oh, you can look at here at the. Yeah, okay. Right?
Yeah, I was just doing.
You can still use calculator. I said to you, so that you can still use calculator. If sitting in front of thing that is more powerful than the calculator, plus you have your phone, which is more powerful than the calculator. It has a calculator. So why you carry calculator? That's what I'm asking. You carry your phone or not?
Because I am more used to doing matrices on this than I am.
No, I'm saying you carry your phone, right? So why do you use an extra device now? Your phone has everything, right? You can download the app for this and then use your phone for that. The TI has their app. Yeah, TI has their app. I'm assuming TI have their app, and you can do the whole TI on your phone. You can download their app. You don't need two devices. Nobody need two devices. You can download Octave or MATLAB is Octave. Even Octave is like $2 or something. Somebody downloaded Octave? Well, you can use online for sure. But when I used online on my Android phone, it doesn't work properly. Now they do have app. Desmos? Okay. It's the same thing as Octave. Okay. No, I'm just not. I'm not saying just solve and start talking about the whole programming language. Like MATLAB is the whole programming language, right? But when I use Octave Online on my computer, on my phone, it's not working properly. Yeah. So, but they also have app though. So I was using online version, but I don't know if app works properly. Someone did you download the Octave app? Okay. Yeah, I'm thinking to just it's like a couple of dollars. I'm thinking to buy it and then try that on my phone as well. Because again, to me now, carrying a calculator in addition to your phone is redundant because you can just use your phone unless you want to save your battery, but that's a different thing. But you can charge your phone anywhere. I understand, man. You're in technology program. If you're not going to use technology, then yes, yes, yeah. How do I go about assigning the voltage and current direction? You can assign. So remember the derivation that we did, right? The derivation that we did is based upon that it's a series circuit and it is flowing in one direction. And then we wrote down the equation based on that and all those things. So you can assign any direction. But if you are going about using the results that we got, then you have to be careful as what is positive, what is negative in general. In this case, of course, you're not writing the equation in this case. We have the equation, we are just using the only thing that you're using it for is this. Now, I can assign it positive, negative, and keep it as negative 12. So all the direction are going to be in accordance with the derivation, positive, positive, and positive. But then I'll have to just use negative 12 for VC instead of positive 12. Your KVL equation will still be VC plus VAR plus VL is equal to 0. And VL will be negative VC minus VR. But negative VC is still going to be negative of negative 12 if you change the direction of VC. So it's going to come out to be, yeah, it's going to come out to be positive 12 anyways. So it doesn't matter in this case, basically, or any case per se. But the idea is that if you have a natural circuit, of course, the current is just going to take one direction. So this is positive VR, positive VL, and positive VC. Once capacitor will charge, then it's going to be positive here and negative here anyways. And if you look at the final, like, oh, well, we don't have the capacitor voltage expression anyways. We have only the current. Okay, so inductor voltage, that's another thing we need to find out in this case. Oh, Rasha, right here. For, yeah, yeah. Okay. All right. Yeah. Let me make sure that I have R over 2L, 1 over square root of LC. Yeah. I think this is okay. Okay. Question. How are we going to find now the voltage expression across the inductor? VLT. How are we going to find that? Take the derivative of what? V is equal to LDI or dt. That's one way to do it. Then the other way, there's another way to do it is what? Is that equation. But I think that taking the derivative is easier, because in the equation, again, if you're using this equation, that is VL is equal to VC minus VR. VR is easy because we have I, but finding VC means that you have to integrate the expression for current, right? So in this case, what you said, it's easier. You take the derivative of the current and find VL. But you have two ways to calculate the value of VL. Okay, when you take the derivative of this equation, or rather, I'm just, it's easier to take derivative of a e to the power s1t plus a e to the power a2. I'm just going to take the derivative of that and then plug in the numbers. The derivative of generic equation overdamped is going to be a1 s1 e to the power s1t plus a2 s2 e to the power s2t. I don't like to keep repeating numbers over and over again. So now we can just go ahead and plug in the numbers. Let's calculate that. The first one is L times A1 times S1. L times A1, my A1 is Q1. Q1 times S1. Negative 1.7889. Negative 1.7889 e to the power negative 0.382t. And A2 times S2 times L. A2 times S2 times L is 1.7889, which is opposite of that, of course, because eventually current is going to go down to 0. Or initially negative, what was that? Negative 2.68, negative 2 volt P greater. This result actually showed you an important aspect of the circuit. At t is equal to 0, the voltage across the inductor is 0. Why it is 0? Actually, it is 0 because of the second equation that we found. At t is equal to 0, capacitor voltage is not going to change. Inductor current is not going to change. So the capacitor voltage becomes equal to the voltage across the resistor drop. These two will balance each other, and there is no voltage drop across the inductor initially. And that's what you see in the inductor voltage equation. If you put t is equal to 0 in the inductor voltage equation, then you're going to have negative 1.7889 and positive 1.7889 at t is equal to 0, which will cancel each other. That shows initial value of the inductor voltage is going to be 0. But remember, inductor voltage can change instantaneously. Here, of course, it's not, but it can change instantaneously. Capacitor current can change instantaneously, and inductor voltage can change instantaneously. But this result confirmed our second equation that we had, that this is equal to 0. All right, any question about that? Now, actually, if I ask you, let's extend it a little bit. If I ask you, let's say capacitor voltage, if you want to calculate capacitor voltage as well, who's going to tell me how I'm going to calculate the capacitor voltage easily? Yeah, right there. From this equation, we know inductor voltage now. We know the voltage across the resistor, so we can easily find out what is the capacitor voltage. Capacitor voltage is VL. There was a question somewhere. Somebody was asking me a question. You were asking a question? Yeah. It can change instantaneously, but its voltage cannot change instantaneously in a series circuit. Yeah. Well, no, they're not the same. Capacitor voltage, zero positive is going to be the same as zero negative, and inductor current will be the same at that. So these two quantities are not going to change instantaneously. Now, if you have other resistors in the circuit or whatever, then their voltage is going to change. The resistance current may change based upon how the switch are oriented and all those things. But these two quantities are not going to change. What do you mean when you say these are the same? It is a series circuit, yeah. Through each component, yeah. Yeah. It did change. Capacitor voltage cannot change instantaneously. Capacitor current went from 0 to IL because it's right, because it was open, and that open is not going to, well that voltage that it had across the open capacitor, 12 volt, that is not changing. But yeah, but I0 at I0 positive, capacitor current becomes 2 ampere, from 0 ampere to 2 ampere. So it did change instantaneously. Yeah. Okay, so the capacitor voltage is going to be VL plus VR according to the directions that we are taking in the circuit. Negative VC plus VR plus VL is equal to 0. So VC is equal to VR plus VL. So capacitor voltage equation is going to be VL, that the equation that we just had. L1, let me write this down then. LA1, because we know the values, but I don't want to keep repeating the numbers. ES1T plus LA2S2, ES2T, that's the inductor voltage. And then how are we going to find the resistor voltage? I times R. So I, of course, is this. And this is A e to the power S1T, A1 e to the power S1T plus A2 e to the power. So R times A1 e to the power S1T plus A2 e to the power S2T. VR is equal to I times R. And now we can add the same terms together, which is LA1S1 plus RA1. Let me go ahead and do it in MATLAB. Let me do A1 is Q1 and A2 is Q2. That might be easier for me. Okay, so L times A1 times S1 plus R times A1. That's 12.261 e to the power S1, and my S1 was negative 0.382, negative 0.382 T. And we know that the second term should be negative 0.261 because VC0 positive is 12 volt. But just to confirm that, let's go ahead and calculate that. L times A2 times S2 plus R times A2, and that's negative 0.26. Negative, what is the value of that? 2.618. And again, observe at t is equal to 0, 0 positive, the voltage value is going to be 12.261 minus 0.261, which is 12 volt, which is the value of the capacitor voltage at t is equal to 0 positive, which is the same as t is equal to 0 negative. All right, guys, any question about this? Once again, remember, irrespective what type of damping do you have, your procedure is still the same, right? Your shape of the equation will be different. Underdamped, of course, is going to be e to the power st a1 cosine omega dt plus a2 cosine sine omega dt. But the process that you're following to find a1, a2 is still going to be the same process. So it doesn't really matter, we are not doing some damping type or we are doing some damping type. It does not really matter. This process is not going to change. However, you have to again, look at the circuit, what is given to you after t greater than 0 when it becomes natural. And then from that circuit, you decide how you're going to write the equation when you're finding the values of A1 and A2. Okay, let's go ahead and take a short break, 10-minute break, and then do some more problems. Perhaps I'm going to start the complete circuit, complete response, because it also has the natural response. Complete response has embedded natural response. So few problems on those should cover both topics. So let's take a 10-minute break and then restart. Okay, let's do the second problem. It's still natural circuit, and then we're going to do the complete response after this problem. Okay. So once again, once you draw the circuit, if this circuit is given to you, make sure you observe it and decide that after the change, circuit is a parallel RLC circuit or series RLC circuit, because based on that, you're going to calculate your omega naught, alpha, and everything, damping type, and all those things. Of course, you can see the change. It's pretty clear that the switch is going to open at t is equal to 0. Before that, the switch is closed. And once the switch is going to open, of course, R3 is going to be out of the circuit, and you will be left with R1, R2, L, and C, and that will make a series RLC circuit. So these things are important to observe again, because if you don't and you start solving it as a parallel circuit, everything is going to be incorrect. Yes, Natasha. R3. Okay, what's the first thing that we do? We find the initial conditions. Okay, who is going to tell me IL0 negative and VC0 negative? So we are finding the initial current through inductor, initial capacitor voltage, and these will not change at 0 positive. All right, who's going to give me a second? Who's going to tell me how to find IL0 negative? Yes, Chris. No. Yes, Mike. R3 over R2? R2 plus. I thought you said R3 over R2. Yeah, it's going to be Vs over R3 plus R2. Inductor, remember, is short circuit. Capacitor is open circuit. So no current is passing through R1 and capacitor. All the current is going to pass through R3, R2, and inductor. Inductor is short, so inductor current is simply Ohm's law, Vs over R3 plus R2. Let me put values in my. Okay. R3 is 100. R2 is 50 and R1 is 50. Vs is 20. Capacitor is 1 micro and L is 200 milli. So IL0 is Vs over R3 plus R2. R3 is undefined. Why R3 is undefined? Oh, because I did not define it. That's why it's undefined. R3 is 100. Okay. Okay, IL0 is Vs over R3 plus R2, and that is 0.1333 or 133.3 milliampere. Okay. Yes.
Is how I imagine it. is zero, the capacitor would drop, and then switch would be open. So
Switch is not open, switch is closed right now. We are finding at t is equal to 0 negative. So switch is closed. It's before time t is equal to 0. Yeah.
my friend
That's going to be at t is equal to 0. Right now we are at just before 0. Yeah. Okay. Capacitor voltage there is. How are we going to find capacitor voltage? What will be the capacitor voltage? How are we going to find it? Very good. And how are we going to find that voltage? Okay. So you're, okay, say it again. So that voltage is going to be, equation, give me the equation. Very good, excellent. That's gonna be IL times R2 at 0 negative. Because again, capacitor is opened, inductor is short. So basically voltage across R2 is the same as voltage across capacitor. No voltage drop in R1, no voltage drop in L. So this is going to be IL0 positive times R2. That's VC0 is IL0 times R2. And that's 6.667. Yes. Voltage divider to do what? How are you going to apply voltage divider? Give me the equation for that. That's not voltage divider. That's Ohm's law. We found the current using that. That's Ohm's law. Right here. That's what we use. Okay, so these are my initial conditions. And now I have my initial condition. Now I'm going to evaluate when the switch is going to open, that is at t greater or equal to 0. T greater or equal to 0, switch is going to open, and my circuit is going to be a natural circuit with R2, L, R1, and C. So let's draw that circuit. R2 and L, and R1 and C. My current is not going to change instantaneously. My voltage is not going to change across the capacitor instantaneously. However, capacitor current will change instantaneously. That's going to be the same current as IL at 0 positive. But VC0 positive is going to be the same as what we calculated, which is 6.67 volt. And then current is going to be 133.3 milliampere passing through each component at 0 positive. Okay, now the damping type first. So let's calculate the damping type. Of course, the resistance is going to be the combination of both R1 and R2. In this case, equivalent resistance. R1 plus R2, L and C. Okay, so let me copy these results that I have. Oops. go ahead and do this first. Wow. I'm going to redraw it, so don't worry about it. I'm just going to put my results and then draw the circuit. Okay, so R2L, R1NC. All right, what type of damping do we have? Underdamped circuit, very good. Underdamped circuit, alpha is less than omega naught, and the two roots are complex conjugate root. So we're going to write down the generic expression for underdamped circuits. ILT is e to the power negative alpha t, a1 cosine omega dt plus a2 sine omega dt. Omega d, of course, is right here, 2222 radian per second, radian per second, radian per second, radian per second, hertz, and seconds. Okay, and again, alpha we know, omega d we know, a1 and a2 are the ones that we need to know. Apply the same thing, start with the initial condition. IL0 positive is going to be a1, cosine of 0 is 1, sine of 0 is 0. So a1 will be equal to IL0 positive, and the value of IL0 positive that we calculated is 133.3, 0.133 is a1. And now we are going to differentiate the current and then evaluate again at 0 positive. All right, anyone remember what we're gonna get at 0 positive instead of doing the differentiation and all those? Anybody remember that equation? So it's gonna be negative a1 omega d sine omega d plus a2 omega d cosine. So the cosine term is going to be 1. So from the first, I would write down a2 omega d a2. And then I'm going to take the derivative of this negative alpha e to the power negative alpha t. And this will stay the same. So the cosine term is going to be 1. Exponent will be 1. So I'm going to have negative alpha a1. This is, as I discussed with you last on Monday. When you take the derivative and put t is equal to 0, you're going to get pretty much a standard equation, which is omega dA2 minus alpha A1. So I don't really want to go and do it again. We have done it several times. You can do take the derivative and then put t is equal to 0, and you're going to get that expression. So make sure you do that. Show the derivative, then put 0, and then you will get that expression. I'm just going to save some time and not do it at this time because we have done it at least 2-3 times. Yes. I expect that you show. Yeah, I don't expect that you memorize it. I expect that you at least show one time. that you are taking the derivative and then putting 0 and you're getting this expression. Okay. And again, use variables because variables make life easy. If you start using numbers right from the very get-go, then you're going to be multiplying number, dividing number, and wasting time. So as you see, I use variables and they're quick. Yes. Yeah. No, what I'm saying is when you take the derivative of that equation and then put t is equal to 0 and show that your result is going to be this. That's what I'm saying. Okay. Yeah. In the homework and stuff, I mean, you can do some practice in the homework, but if you have 3 problems in the homework, then you can show for 1 problem and then the other 2 problem you can just use the expression. That's fine. Right? Because that's where you're using simple differentiation and stuff. And one of the requirements for the ABIT is that for the bachelor's student, they go beyond college algebra and they do know how to do differentiation and integration. That's one of the requirements. So when we have to demonstrate to them that the students are doing simple differentiation integration, then these are something that we can pull and show them that, hey, students are doing differentiation and stuff. Now, if you just go ahead and write down the result, then you're not showing it. You're just putting the result down. So that's why it's important. Again, this is not difficult. We have done it several times. But right now we are saving time, and I don't want to do that over and over again. Okay, now we go back and see what is dIL over dt. Of course, dIL over dt is inductor voltage at we are evaluating at 0 positive over L. We already know the value of A1, so A2 will be, of course, this plus alpha A1 divided by omega d from this equation. Okay, now let's go back and check our circuit. So we are looking for VL0 positive. So this is VL. All right, so I'll keep this VC, and then we have VR1, and then we have VR2. And again, if you want to change the polarity of VC, by all means, you can do plus and minus. Just make sure that the initial value that you found out for VC is this. So if you do change the polarity, then you have to use the negative of whatever the value we had. What value did we find out? 6.67. So you just have to find, you just have to use in the equation negative 6.67 if you do change the polarity and put positive here and negative. That's the only difference. Okay, so now from this, what will be VL? Equation for VL? Okay, so VL minus VC plus VR1 plus VR2 is equal to 0. So VL is going to be VC minus VR1 minus VR2, right? VC minus VR1 minus VR2. And that's what we're going to use. VC 0 positive minus VR1 0 positive minus VR2 0. The dA2 minus. All right, VC 0 positive, we already have the value. We calculated at VC 0 negative. So that value is the same as VC 0 positive. How are we going to calculate VR1 positive and VR2 0 positive? Who's going to tell me that? Yes. Someone was running. Oh, no. Yes, sir. You were saying something? Oh, okay. You're just scratching your head, Gloriana. How are we going to just scratching your head? You should not. Okay. If you're scratching your head for this question, you are in trouble. I'm telling you that. Yes. Yes. Huh? Okay. And okay, so you're applying Ohm's law. Yes, we're applying Ohm's law basically. So if you're having a hard time to apply Ohm's law, you are in trouble. Remember that. So VC 0 positive minus IL 0 positive times R1 minus IL 0 positive times R2. So I'm just going to go ahead and calculate the value of A2 from this equation. Instead of further simplifying this, A2 will be equal to, let's see. So what A1 is, A1 is IL0, right? IL0 is A1 and A2 is VC 0 positive. So VC 0 minus IL 0 divided by R times R1 times R1 minus IL 0 times R2 divided by L. That's going to be plus alpha A1 plus alpha times A1. And the whole thing is divided by omega d. So the whole thing is divided by omega d. It's syntax error. Oh, multiplication. Sorry. Okay, so A2 is coming out to be 0 for me. Check if your A2 is 0. Getting 0? Anyone else? Yes, anyone? Is that correct result or incorrect result? Let me know. Can you see the circuit? Circuit is on, go up. This circuit? Okay. Getting 0? 0. Good. That should be milliampere instead of ampere. Put it down in. It should be milliampere. Milli. Okay, and again, the initial value of the current, as you can see, at t is equal to 0 positive, exponent is going to be 1, cosine will be 1. that will leave you to 133.3 milliampere, which is the initial value of the inductor current. And then the inductor current is going to oscillate and dissipate. It's going to oscillate because the frequency, natural resonant frequency, is much larger than the time decay. So it's going to oscillate and then it's going to dissipate. So if you want to plot this current, we define the time first, time 0 to, usually we use settling time, but we can use, of course, time constant as well, 250, 1 over 250 as our time constant, and plot it for about 5 to 6 time constant. So let's say if we define our tau is equal to 1 over 250, 1 over S, 1 over A, and then define our time as 0 to divided into 100 points per time constant and go up to, let's say, 6 times constant. I don't know if it's going to be settled down in 6. I'm assuming it would settle down in 6. And then the equation for I, which is A1 into exponent of negative or exponent of alpha times t, since alpha value is positive, so I'm going to put negative alpha times t times cosine of omega d times t. Then we plot that time and current. Let's make the line thicker a little bit. Line width 2. So this is the part of the current. Let's go ahead and copy this as well. This is how current is. Starting at 0.133, that is the initial value, and then oscillating multiple times. It is oscillating because your omega d is much larger than your the exponential decay. So if this frequency omega d is quite large, then it's going to oscillate multiple times. If it is not large, then it's not going to oscillate much. It may oscillate one or even not once properly. So omega d represents the oscillation frequency. If it is large, it's going to oscillate many times. And as you can see, I did not do the settling time, but I just did 6 times the time constant, you can call it. And it's almost 0 by that time. Settling time will be actually smaller than that. Anybody remember what was the definition of settling time that I discussed on Monday? Yeah, so settling time is when the response is going to drop down to about 1% of the peak value and never goes out of that 1%. So that time is the settling time. Yeah.
Just for my part,
You have what? Yeah, that's not, I'm getting. That's 0. That's 0. Yeah, 4.5 exponent negative 5 is as close to 0 as possible. Although, yeah, because again, I'm just using the values that are in MATLAB, so not rounding up or anything. If you are rounding something, then it's possible you end up with a very small number because of that. Yeah, not 0. If it's a big number, that's a problem. But if it's like micro, exponent negative 7, exponent negative 5, that's the round off error. That has to be round off error. Yeah.
but it's
just drop it as 0. Just put it at 0. If it is that small, just put it at 0, because the first term is much larger than the second term in that case, right? So even if you add both terms, the second term is not contributing anything. Yeah, it's irrelevant. Okay, guys. So this is this. Oh, one thing was left. I think I'll leave it to you because I want to jump to the second thing that we were supposed to do is the capacitor voltage expression. Now you tell me, how are we going to find the capacitor voltage expression? How are we going to find the capacitor voltage? Yeah, it's written, it's written over there. It's written there. What I'm asking is written here is VL plus VR1 plus VR2, of course. Now, once again, guys, if it is written, everyone think, oh yeah, it looks very easy. We can do that. If it is not written and I ask you the same question, everyone is going to be lost. So just make sure. Again, I cannot spend 5-10 minutes on those things because again, we don't have that much time. So that's VLT plus VR1T plus VR2. All right, who's going to tell me how are we going to find VLT? Now it's not written, so everyone is quiet. Take the derivative of the current, yes. LdIL over dt. Okay, what about VR1T? ILT times R1, and the same thing was IL2. So we can just write down IL1 times R1 plus R2. Okay, I'm not solving it. Make sure you solve it and then find the expression for the capacitor. So I'm just going to write down, finish it. You have the current expression, take the derivative of that, multiply by L, and of course that. So it's very easy to solve and find the expression for the capacitor voltage. And when I put finish it, make sure you finish it so that you can get practice. If you just, many times you never open the notes, what we are doing in the class, you just go close it, and then next time you come, then you open the notes. Because if you do go through the notes, then you will be well prepared for the next lecture. But many times I have observed students only open their notes in the class. All right, now we're going to go to the next topic, which is the complete response of RLC circuits. Okay, before we discuss this topic, let me ask you this. When we were discussing the complete response of RL and RC circuits, which are called the first order circuits, because the equation has single order derivative. As you saw in RLC circuits, the equation that we write, it is second order derivative. That's why they call second order circuits. For the first order circuit that we learned, RL circuit and RC circuit, when we found the complete response, which is also the forced response, that is, your source is also present after the change is happening. What was the methodology that we follow to find the complete response of RL and RC circuit? What did we use to do? Who's going to tell me? Say it again. Very good. Excellent. 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 So you have to find two components. You have to find the steady state component of that variable, whether it's the capacitor, voltage, inductor, current, or whatever. And a steady state means that you let the circuit run for a very long time, assume capacitor is open circuit, inductor is short circuit, and see what will be that value. That's the steady state value. And then you write down the expression for the natural response. Now, in this case, natural response depends on the damping type, remember. So you have to find the damping type of the circuit. And damping type you find out by removing all the sources. You have to make the circuit, or you have to imagine, you don't have to physically remove it, but you have to, in your mind, assume no sources are present, and then see if it's a parallel RLC circuit or series RLC circuit. and then from that you find the damping type, and then write the expression, the damping expression for that. And then you solve that basically for the unknown coefficient using the initial conditions. So method is the same as we followed in RL and RC circuit. So complete response for parallel RLC circuits is going to be, first we calculate, let's say, capacitor voltage. That's going to be the capacitor voltage steady state value, capacitor voltage natural response. And again, a steady state value is capacitor voltage when time hits infinity, and the natural response depend on the damping type. So we have three different natural response expression based on the type of the damping. So that we can find first, and then from that we can find current and all those things. And for the series, we go usually for current because current is the same passing through each component in a series circuit. So it's going to be ILT is equal to IL steady state plus IL natural response. IL when T is going towards infinity, that is inductor is short and capacitor is open. So that is going to be the methodology, and exactly the same as we did for the single order circuit. Okay, so complete response is also called, again, forced or step response. Complete is also called forced response or step response. So all three names are for the same type of setup: forced, step, or complete response. Okay, let's look at a circuit. What do I have? We're going to start solving. This is going to be our third problem, problem 3. So this is my circuit. And let's see. I'm sorry? Yeah, resistor 3. That's going to be resistor 3. Resistor 3 is 1 kilo ohm. Okay. So we are going to find ILT, and we're going to find C. So the first thing, of course, we are going to do, again, you can see the switch is going to open at t is equal to 0. So the right hand circuit is just going to be separated from the circuit. And what type of circuit is this, parallel or series, after the change is going to happen? It's going to be a series RLC circuit, of course, because you have R1, L, R2, and C connected in series with the source. Of course, source is not going to go anywhere in this case. But when you are calculating the damping type, then you have to shut the source down and then think about if it's parallel or series. In that case, it's going to be a series circuit anyways. So the first thing we are going to do is we are going to calculate the initial conditions, because we know we need those conditions in order to calculate the A1 and A2 values later on. So initial conditions at t is equal to 0, negative. Okay, who's going to tell me IL0 negative? Just before the switch opens up, how are we going to calculate the current? Oh, it's not here. Broadly is not here, and Taylor is not here. Okay. Yes, guys, quickly. Don't take that long. Very good. Capacitor opened, inductor short. So the inductor current, or IL, in this case is going to be simply Vs1 minus Vs2 divided by R1 plus R2, Ohm's law. And once again, if you're struggling, you have to do a lot of work. That means. Let me put everything in my MATLAB so we can do it quickly. Clear CLC. Vs1 is 10, R1 is 1.2 exponent 3, L is 100 millihenry, R2 is 800 ohms, capacitor is 100 nanofarad, resistor 3 is 1 exponent 3, and Vs2 is 5. Okay. So IL0 is Vs1 minus Vs2 divided by R1 plus R3, R1 plus R3. 2.27 milliampere. 2.27. I'm sorry? R1 plus R3, R3 is 1 kilo, right? R2 is, oh, in the expression. Okay, sorry. R1 plus R3. Yeah, I did it here correctly, but in the expression, I wrote it incorrectly. R1 plus R3. So 2.27 milliampere. Okay, who is now going to tell me how to find the capacitor voltage? That's not difficult. Somebody should tell me this. Okay, Chris, you go ahead. No, don't tell me it's 5 volt. Tell me how you're going to find it. Okay. Vs1 is parallel with Vc. In which world it is parallel with Vc? Are they connected between the same nodes? Vs1 is connected here. Vc is connected here. Are they connected between the same nodes? Why do you want to say that they're parallel with each other? Yes, Natasha. Vs1 minus Vs2 is Vc. No, it's not. Okay, anyone else? Exactly right. Vs1 minus voltage drop here is the voltage right here. Vs1 is here, VS2 is here. When you subtract these two, how this is going to be equal to this voltage? They're not. I mean, VS1 minus IL0 negative times R1. VS1 minus the drop here is the voltage here. VC0 is equal to VS1 minus IL0 times R1. 7.27 volt. So these are my initial conditions. T greater or equal to 0. At that time, switch is going to open up, and the right hand of the circuit is going to be excluded from rest of the circuit. So we will be left with VS1, R1, L, R2, and C. So let's redraw the circuit. VS1, R1, L, R2, and C. IL and VC. Okay, first thing, oh man, I draw the circuit again, and I may have to. Let me go ahead and clean this up first so that I can post my damping results. Maybe it's easier to just don't erase the circuit. I'm erasing it because I want to copy paste, and it's going to move the circuit here and there if I do that. Okay, I'm going to calculate the damping type now. I have R1, R2 is my equivalent resistance. R1 plus R2 in series, L comma C. Okay, so let's, anyone, what is the damping type? Critically damp, very good. I'm sorry? There you go. All right, alpha 10,000 radian per second, omega naught 10,000 radian per second, omega d0 10,000 radian per second. So critically damped circuit. Alpha and omega naught are same. Okay, let's go ahead and draw the circuit real quick. So I have, what do I have? VS1, R1, L, R2, C. VS1, R1, L, R2, and C. IL and C. Okay, so critically damped circuit. Let's go ahead and write down the expression for now. IL, since it's a series circuit, we're gonna start with IL. ILT is the steady state value plus ILN. All right, what will be the steady state value of the current? Who's gonna tell me that? No, you don't tell me that. Somebody else tell me that. What will be the steady state value of the current? You don't need calculation for that, remember. No, steady state value, not the initial condition. We already have initial condition. What is the steady state value of the current? Mike, what is the steady state value? As time is hitting infinity, what will be the current in the circuit? Huh? From that circuit? Yes, Natasha. No. What? Yes. No. What else? Zoris. Okay, since we don't have time, yes. Glorian. Excellent. Capacitor is opened. Current is 0. Okay, so it comes down to natural response. And since it is a critically damped circuit, then the natural response expression is simply e to the power negative alpha t a1t plus a2, or a1 plus a2t, whatever you're on, right? Because addition is a commutative process, doesn't really matter. Now we have to find a1 and a2. We use the same approach, that is the first at t is equal to 0 negative, or 0 positive, sorry. IL 0 positive, e to the power 0 is 1, t is 0, so IL 0 positive, which will be equal to A2. And IL 0 positive value, what did we calculate? IL 0, we calculated as 2.27 milliampere. So A1 is 2.27 exponent negative 3. And now we're gonna take the derivative of current and evaluate that at t is equal to 0 positive. All right, we take the derivative. First one is going to be negative alpha e to the power negative alpha t, a1t plus a2, and then the derivative of the second term plus e to the power negative alpha t. Derivative of the second term will be a1 times a1. We evaluate this expression at t is equal to 0. So a1, this is going to be 0, and exponent terms are going to become 1. So I'm going to have negative alpha a2 plus a1. Negative alpha a2 plus a1. We already know the value of a2. So from this, we're going to find the value of a1. All right. Derivative of inductor current, as we've been doing, VL over L at 0 positive. All right. Now from the circuit, what is VL0 positive? Expression for VL0 positive. So this is VL, and then this is VR1, and then this is VR. All right. From the circuit, Now I'm going to write down the expression for VL. Yes. Yes. What will be the equation? Hold on. Yes. No, not really. Yes. Natasha, what will be the expression for VL from the circuit? Using KVL, as we already said KVL. Apply KVL and tell me what will be the expression for VL. Minus VC plus VR1. All right, Mike, what will be the expression? Is that VL? I don't think so. Zurez. Okay. Okay, so what will be the equation for VL? You put down the whole KVL. What will be the VL from this equation? Lazaro, what will be the VL equation? Quickly.
So it's gonna be PL is equal to VR2, sorry, is equal to minus VR2 minus VC minus VS1 minus VR1.
No. Yeah, exactly. VS1 minus VR1 minus VR2 minus VC. No, that's not. I don't think that's what you said. That's what who said? You never said anything. No, I don't think so. Did he say that? I don't think so. And if you said that, then you're correct, by the way. I don't want to hurt your feeling, but if you said that, you are correct. I did not hear you. You said that, so that my mistake, maybe. Right? All right. So VL0 positive is VS minus VC0 positive minus VR1 0 positive minus VR2 0 positive over L. And then since we already know what A2 or A1, what did we find out? A2. So I'm going to bring A2 on the other side, plus alpha A2 is equal to A1. Okay. We know VC0 positive. We know VS. What will be VR1 and VR2 0 positive? Quickly, who's going to tell me except you? Don't take any time and tell me what is VR1 and VR2 0 positive. How are we going to calculate that? Using Ohm's law. Exactly. Very good. So IL0 positive times R1, IL0 positive times R2. We're doing this thing over and over and over again, remember, so shouldn't take this time to answer these questions. All right, so A1 is equal to Vs minus VC0. Do I have VC? Yeah, I have VC0. VC0 minus IL0 times R1 plus R2, R1 plus R2, and that divided by L plus alpha times A2. Do I have A2? A2 was what? Oh, A2 is the same as IL. Okay, so that's why I didn't do it. IL0. Let me see, this equation is correct. Seems like it is correct. No, Vs is undefined. Why Vs? Oh, that's Vs1. Is that Vs1? Oh, okay, it's VS1. So VS1. 4.544. Anyone else is getting the same result? Okay. So ILT is what? E to the power negative alpha t. Alpha is 10,000. Negative 10,000 t. A1t plus A2. A1 is 4.54. T plus A2 is, what was A2? 2.27 milli. 2.27 milli. And again, as you can see, 2.27 milli is such a small number as compared to the first number. Then really you can pretty much ignore this thing if you want. And oh, that's the truth. So we should not ignore it. I thought that was constant. You're right. You're right. That's a good catch. So we should not ignore it because that is dependent on time. So if time is small, then this number will be small. Very good. Yeah, but if it's a cosine term or sine term, then if one term is very small, then we can ignore it. Okay, so that is the value of current in ampere for t greater or equal to 0. And since we don't have time to do that, who is going to tell me VCT? How are you going to find the capacitor voltage expression from the circuit? Capacitor voltage expression from the circuit is? How are you going to find that? Circuit is right there. KVL, okay, so what will be the equation for the capacitor voltage? Yeah, we just wrote down that expression. We just wrote down that expression. Vs minus VLT minus VR1T minus VR2T. Vs, inductor voltage, of course, is LDI over dt. Current equation is right here, so you take the derivative of that, and that's going to be IL T times R1 plus R. And again, you got to finish this since we don't have time to do this. Finish it. And when I say finish it, make sure you finish it so that you know how to do it. Yes. Yeah, that ILT, that's the equation right there, ILT. Because we are trying to figure out the equation for VC, right? Yeah. Now, if you are finding at any specific time value, then you can always find the current at that time and then put that value. Let's say you're finding what is the capacitor voltage at 10 millisecond, right? So then you can calculate the equation at 10 millisecond and then put that value here. But you will still have to first take the derivative of that and then put 10 millisecond to find the voltage of the inductor at 10 millisecond. But here you can put 10 millisecond directly then. You don't have to write the equation. Yes. The steady state value of VC is going to be Vs because it is going to open up eventually and no current will be flowing in the circuit. Therefore, Vs1 will be equal to Vc.